So this is the lab for the specific heat capacity. And I'm going to scroll down. This is actually the equipment that we would be using. So you see the ice tray here because we're trying to use really cold water. So I put some ice in the water to actually get it down to almost 0 degrees. Thermometers, of course. Oh yeah, there's a scale here. I was thinking, why is there a spring scale? And then there must be another scale somewhere else. Well, because we have to figure out how much these metal pieces are weighing. We're also using a graduated cylinder to figure out, and by the way, there's another scale here yet. We're also trying to figure out, sorry about my phone ringing, we're using a graduated cylinder to figure out how much water we put in. Usually I like to use as little water as possible and as much metal as possible because water has such a high specific heat capacity. To actually see a difference, you need as much metal as possible because they have such a low specific heat. And I also like to use a large temperature range, so I like to heat up the metal as much as possible to 100 degrees Celsius and use really cold water, and then vice versa, put the metals in the freezer. But of course I'm not going to do that here in this applet portion. I'm kind of restricted to the applets that I have at hand. This would be the experimental procedure. I actually call this particular lab the error lab, tongue-in-cheek, because when you actually do the experiment with getting the metal from the freezer, put it into the styrofoam cup or the calorimeter, and then pouring the water in, there's all kinds of errors involved. Experimental errors that just throw it off, that usually we have kind of like in the neighborhood of 20 to even 50% errors in there. And regular lab manuals acknowledge that actually. In this particular case here where I'm using these applets, we will actually get perfect, almost perfect numbers. I will show you that later. But anyway, actually here they are. Here are typical errors. These are actually on the low end, 5% and 23%. Basically what we're doing is we're calculating the heat flow that goes, for example, from hot lead into cold water, and these two heat flows, of course, should be the same in joules. That would make sense. It's the conservation of energy. Heat is energy. So in this case here, I would start out with lead at 99 degrees Celsius with really cold water at 4 degrees Celsius. The lead has a mass of 361 grams, the water 100 grams. Actually, when I do it these days, I like to actually use only 50 grams, as little as possible, as I said. And then, so I plunge it in there, and then the water gives off heat, but the lead has such a small specific heat capacity compared to the water. Water, among all common materials, has a really high one at 4,186 joules per kilograms in Celsius degrees. So therefore, the mixing temperature only actually goes to 13. So the water's temperature as it absorbs heat from the water doesn't get up very high, 4 to 13. That's again why I like to use a large difference in here and a large difference here as well, so that I can actually see a difference. Notice that I'm down to actually just one significant figure basically. So the water temperature only goes up by 9, while the lead temperature actually goes up by 86, even though it has 3 times the mass. Again, it's the large specific heat capacity of water that does that. And then I did it here for brass, and you can see here the numbers. Again, this is the heat flow. Again, these two heat flows should be the same, but of course, with all these errors involved that I mentioned, by the way, they're also listed in the post lab, you get, not perfect numbers. And again, for the applets, actually, we probably will. Okay, these are the data tables. They're going to look a little bit different on the revised lab sheet that I hand out. I'm not going to use the freezer with the applets. And again, you will actually get really tiny errors because the applets provide perfect data. They don't simulate in a real experiment, as in that you have a lot of measurement errors. So I meant to mention here, table 2 is cold specimen, hot water, and then table 3 is hot specimen, cold water. All right, and then we're going to skip the conclusion, so you don't have to do that one. All right, let's start with the applets, and I'm going to do table 2, cold specimen, hot water next. recording for the cold specimen and hot water. I'm doing this alphabetically, so I'm going to use copper first, and I want to have a cold specimen. So the coldest temperature is 20 degrees. I wish it would get colder, but I can't, I guess. The applet restricts that. And as much metal as possible, as little water as possible, and here the highest possible temperature is only 40 degrees. So then hit start, the copper piece goes in, and we can see what happens to the water temperature here as they're mixing. So water temperature, of course, goes down while the metal temperature goes up, and I will record these numbers. I like to have as much metal as possible because metals have a relatively small heat capacity, 385 joules per kilogram in Kelvin or Celsius degree. The Kelvin or Celsius degree for temperature difference is the same, so it doesn't matter, but this here does matter, grams versus kilograms. The way you should usually see it listed is 385 joules per kilograms in kelvins. And water has a really high one, 4,180. I also see numbers 4,184, 4,186. So water has a very high specific heat capacity, which is why I like to use as little water as possible. Notice that the temperature of the water actually only went down by 5.5 degrees, while that one of the copper piece went up by 14.6 degrees. Again, due to the large difference in specific heat capacity, despite that I actually used 4 times the mass for copper as I did for water. Okay, I'm going to reset this. Let's see, again, alphabetically, gold is actually next. So as much mass as possible. It's cold, so as little water as possible. Actually, no, I can't change this. And then the temperature as high as possible. Unfortunately, again, it's only 40 degrees, so there we go. In the meantime, I'm jotting these numbers down. The water does contain a lot of heat, but gold doesn't need that much heat to actually heat up because its specific heat is really small, 128, which is, by the way, the same as that for lead because it has a very high density. They're related. Compared to water's 4,186, and so it only needs 1/30 of the heat that compared to water in order to heat up. Okay, next one. Still alphabetical. Copper, gold, iron. There you go. Mass, and here the temperature. There we go. So 452 joules per kilograms in Celsius degrees or Kelvin. And I just chose iron. And the last one to choose, I believe, is silver. In the real experimental lab, we don't have silver or gold. We do have, obviously, iron, copper, aluminum, tin, things like that. All right, so the mixing temperature is pretty much 34.0. Okay, and I'm going to do just one more, which means I'm going to cut the table short in the lab manual because I only have these choices. There we go. That's silver. 34. Specific heat capacity. And the mixing temperature is, let's call it 36.3. I did find a couple of other applets. Here's one. But it only works with hot metal, so if I reset this here, where's the reset button? Oh, there it is. I can only work with hot metals and cold water, but not the other way around. And then here's yet another one. And here it's kind of the same thing. If I try to choose hot water here, I can only choose another liquid. It doesn't give me I think it's right here. Yeah, all of a sudden it doesn't give me the choices. Anyway, these 4 metals that I got for this one here, that's good enough for this table. So this is going to be an example analysis. I'm just going to show you the first data here from what I just measured here, how to compute these. This is actually the revised lab sheet. There's not much change. On this one here, I left out the last 2 rows there, and then whatever my measurements are, I put them in a font. So I wrote them already down here, but I put them in a font as if they're handwritten, so to say. I'm going to use a calculator here in order to show you that, but I do have to actually, this table 2, cold specimen hot water, I do have to scroll up a little bit because otherwise my calculator is not going to completely fit on here because I need to see the numbers. So, which is a good thing. I'm only going to do the first one here. So I have 34.6 degrees was the mixing temperature for copper with an initial temperature of 20. So it gained 14.6 Celsius degrees, while the water obviously here gave off minus 5.4. I don't know why I just did that. And I think I fixed that. And then what I have to do now is I have to multiply across. The equation is on the top here. So the delta T that I have here times the mass measured, but I have to convert that one to kilograms. So I have to divide by 1,000 times the specific heat capacity, 385 in this case for copper, gives me the heat flow for that, for copper, how much goes in it. And then I do the same thing for water, the temperature drop times the mass, again divide by 1,000 to get it to kilograms, times its specific heat capacity, then will tell me how much how much heat flew out of the water into the copper. Okay, again I need to scroll that up a little bit so that my calculator actually fits here. That looks like the last time I used this one here was for actually the heat expansion of metals. Anyway, so 14.6 times 120 divided by 1,000, again grams to kilograms. Of course, if you want, you can write 0.12 right away, times 385, and I get around it 680. Let's do 2 significant figures, 680 joules that flow into the copper. Let's do 2 significant figures here. Over here we have 3. This one here only looks like 1, but notice that when I use the applet, actually I was able to adjust it to the closest degree. So we actually do, it's not a rounded 40 or 20, but it really is actually 20. So let's use 2 sig fig here, and that reduces everything to 2 sig fig, so 680. Okay, that's the amount of heat that flows into the copper. The amount of heat that flows out of the water is negative 5.4 times 30, again divide by 1,000 to get it into kilograms, times 4,186. Sometimes you see 4,180 or 4,184. I really don't know why there was like a tiny difference at the end there, but it really doesn't matter. It's that one is actually such a small discrepancy, it really doesn't matter. Hit enter, and not surprisingly I get virtually the same number. So 600, did I say 670 rounded earlier? That's what I meant. If I said 680 accidentally, apologize. And then here it is negative 680, so that's what I'm going to plug in here. So 670, 680, and then I compute the error. A quick way to compute the error is actually take the 680, forget about the negative there, and divide by the smaller number, and then don't pay attention to this one here. This is actually 100% right here, but it's this one here. This is 1%. I know it says 1.5% perhaps, but let's just call it 1% error. And again, as I mentioned earlier, because these are data from an applet, these are kind of almost perfect data. So aluminum, and I like to use as much mass as possible. Unfortunately, it tops out at 50 grams, and then as high temperature as possible for the hot metal. I'm going to show the specific heat here. It's actually 903 joules per kilograms in Celsius degrees. Then I have to click next. I'm going to choose a liquid. I'm going to use water. Here I'd like to choose as little water as possible. Unfortunately, it's the same mass of water, so the end result will be just that. I'm going to start this one here. The end result will be just the ratio of the heat capacities. For water, by the way, it's 4,184 or 4,186. I see both numbers. Joules per kilograms in Celsius degree. Notice that when you compare these two numbers here, this is about 4 times as much, which means that the temperature drop for the metal should be about 4 times as much. And I think we can see this one here. So from 200 to 50 degrees, that's 150 degrees Celsius in drop, and for the water it's 30. I'm sorry, from 20 to 50 is about 30, so yes, it is about 4 times as much for the metal. Water contains a lot more heat at the same temperature. Metals actually have a relatively low specific heat capacity, so they're really easy to heat up to a high temperature. They don't need much heat. I'm just going to show the graph view and the microscopic view here. I don't know whether I don't have it turned on before. I'm going to push this over a little bit. And so here you have the hot metal and the cold water, and they're in contact. And of course, the hot metal gives off energy to the water molecules that are close to it, and therefore they start to vibrate more, while they start to vibrate less because they just give off that vibrational energy. And then here, of course, we see the temperature of the metal going down and temperature of the water going up until they meet and are in thermodynamic equilibrium, meaning they're at the same temperature. If one of them gets warmer, it has to give off energy because due to the contact here, it has too much vibrational energy, it will give it off until the temperature is the same. All right, let's do the next metal. I'm going to choose, again, I do this alphabetically, so it's going to be copper, according to the English alphabet. So it's much massive possible. It's still 50, highest temperature possible. I show this one. This is so 385. Then I'm going to hit the next button, and I'm going to choose same water again. I'm not going to use ethanol. And as little water as possible, and I guess 20 degrees, that's it. There we go. And, oh, I have to hit the next button and then start it. And there goes the copper, nice piece of copper there. And let's see what we measure. All right, and then of course if I did the show graph here and show microscopic view, it's going to be the same thing. All right, let's do the next one. Nope, actually, I want to choose a solid. And we're going to do, let's see, iron would be the next one alphabetically. There we go, there, 449. And, oh, next button, water. Mass. As little water as possible because of the very high specific heat capacity, because otherwise the temperature increase for the water would be so small that we wouldn't be able to measure accurately. All right, so here we got iron, and it turns out I actually forgot to copy down the temperature difference on the other one, so I'm going to do this one here now, 37.4, and I'm going to pause this here for a moment and go back to replay it just for myself with the copper piece. And one more. In the meantime, I did replay it for myself, and again, I need to choose solid. There we go. Yeah, we're going to use, let's see, we have those, so silver. All these here, 235, then should click next. Choose a solid, no. Choose a liquid, water, as little as possible, show this one, next, and start. Again, trying to get the largest possible temperature difference, get the possibly most amount of metal and the least amount of water, but they don't give me many choices here. Okay, 29.6 is the mixing temperature. And this is the other applet, and I pretty much have the same choice except there's a gold here. I'll use that in a moment, but let's just do the silver and see if we come up with similar things here. So 20 grams, let's see, 120 grams, 30 grams of water, and then here as little as possible, and then start. And yes, here we have a large amount of metal compared to the water, so that's kind of nicer. The mass is 4 times as much, while for the water heat capacity, that's approximately almost 20 times as much. So the the metal temperature should go down 5 times faster than what the water temperature is going up. And we can already kind of see that the difference here is about 160 Celsius, while here it's about 36 Celsius, and that is in the neighborhood of, did I say 4 or 5 times a moment ago. Okay, anyway, I better record these numbers. We can also see that this particular applet uses a slightly different specific heat for silver than the other one, 234 versus 235. I looked up another one here, I think it's this one here, and here it says actually, where'd the silver go? There it is, 233 actually. Again, joules per kilograms, and Celsius degrees or kelvins, that's actually the same. So I don't know exactly why these numbers are just slightly different. Earlier, I saw actually for aluminum 903. I'm just familiar with 900. Anyway, just very slight differences. So let's do the other one here, gold, reset. As much mass as possible, high temperature as possible, water as little as possible, and low temperature, and hit the start button. Gold, by the way, has a very low specific heat capacity. The heat capacity is reciprocal to the density, so the higher the density is, the lower is the specific heat. Lead, by the way, also has a very low one. Aluminum actually has kind of the highest one among metals, as it is the one with the least density. And I actually forgot to show this applet here, so here I'm not going to record these here, so I can use something. Oh, there, look, there's lead, and then I can heat it up. Just have to find that. Oh, there it is. Turn the Bunsen burner on. That makes sense. Of course, it is a Bunsen burner, not anything else. Bunsen was German. So the temperature rises here with the heat from the Bunsen burner, and the metal is in the water, and it tops out 100 degrees Celsius, because that's when water stops heating up as far as temperature is concerned. It still gets heat, but then it starts to evaporate, to boil, and then the initial temperature of the water is this much and this much here, and then I put the metal in the calorimeter, and the temperature starts to equal out, and it's actually very little. Lead has a very low specific heat capacity, so the water really does just rise from 4 degrees to 9 degrees, while the lead temperature goes down from 100 to 9 degrees for 100 grams of lead, 60 grams of water. Again, water has kind of like 1/30 the specific heat capacity of lead has 1/30 the specific heat capacity of water, making meaning that it heats up 30 times faster. All right, so let's evaluate the first line here for the hot specimen in cold water. And so let's do the aluminum. Again, I have to push that a little bit up here in a moment because the calculator needs to fit there. And again, I put these in this strange font, so it kind of like looks like they are handwritten. Okay, so the initial temperature of the aluminum was 200 Celsius, that of the water 20. The mixing temperature was 52. So between these two temperatures, the aluminum temperature went down by 148, and the water temperature went up by 32. I believe you can do that in your head too, probably. And then I multiply across, so it's going to be negative 148 times 50 times 900, and of course the 50 is divided by 1,000 because I want to get in kilograms, and then this one here is 32 times 50, again divided by 1,000 times 4186, and again, in order to actually do that, I do have to push it up just a little bit. There we go. Okay, so that's my calculation from earlier for the previous table. So now I'm going to have negative 148 times 0.05, again 50 divided by 1,000. I can do that in my head. If you want to type it, that's perfectly fine, of course. And I come up with negative, and again, let's call it 2 sig fig, because these are not completely rounded, these 200. It's not 199, it's actually 200. So this is actually 3 sig fig, but this one is definitely 2 sig fig. So it's not 21, it just happens to be 20. And the same thing goes for the masses. So 2 sig fig, let's call it negative 6,700. Then for the water, 32 times 0.05 times 4,186, which means it simply boils down to the ratio of the specific heat capacities. Notice that this ratio is about 4 times as much, which means also that the temperature differences or temperature changes are also about 4 times as much in the other direction. So the aluminum goes 4 times down faster than the water goes up, reflecting the ratio of specific heat capacities. I hit enter, and obviously I come up with virtually the same number, 6,700. So that's, as far as rounded is concerned, that's what I'm going to plug in, 6,700. And that one looks like a 0% error, again, because my data are virtually perfect due to using the applet. By the way, compared to my numbers earlier, where I had this one here for the copper, this is, why is there 670 and the other one is 6,700, 10 times as much? Well, easy to explain. One of the reasons is that the high temperature that we used here is only 40, so the initial temperature difference was only 20, while here it's actually the initial temperature difference is 180, so almost 10 times as much. That pretty much explains most of the difference between this one here and this one here. For this particular one, I could only use an applet that gave me a high temperature of only 40 for the water. Here I was able to get a really high temperature for the metal, so I was able to choose 200. Much larger temperature difference also means that there is a much larger heat flow going on, and again, that's actually what I wanted to kick down the error at the end, that I actually am able to measure the temperature differences better. And that's actually it for the lab on specific heat capacity. Again, no conclusion.